So I'll be just starting from the place where I have just missed my class. Okay, yeah. So so in the morning session, we were trying to do a simple problem where we had a current ratio of 10. Okay, so based on this, we just try to compute the value of delta VBE, and this delta VBE turns around to a value of 59.5 millivolt, okay, which is being evaluated for a temperature of 300 Kelvin. Okay. Now, and also one has to note that this value is evaluated only for a value of n that is equal to 10. Okay. So, and later we just start looking at delta VB with respect to T, so which represents the positive temperature coefficient of value of 0.198 millivolt. Okay. And now that we began with the discussion of delta VBE, which is basically a positive temperature coefficient, and then later we started with the discussion of VB, which represents the negative temperature coefficients. So now that we just need to combine both these quantities in order to create a V reference voltage, which is temperature, which exhibits a zero temperature coefficient. Okay. So with these settings, let us try to first create a reference circuit, which is the V reference circuit, that is first been implemented in a symbolic way. Okay. So symbolically, one could create the structure by having a current source, and that is being passed on to a diode connected configuration, and this diode connected configuration will just create a VBE. Okay. So the one that I am trying to draw is actually generates a VB, or in short it is my negative temperature coefficient term, okay, for a given current, which let us assume that it is equal to I naught. And now we want to add this delta VB term, which actually has the positive temperature coefficient. Okay. So let me use a different color. So we need a PTAT generator, where this PTAT generator produces this delta VB. Now this delta VB has a different coefficient value, right? So what I really mean is that we know that this V reference could be written as alpha 1 times that of VBE in the place of V1, and alpha 2 times that of delta VBE, which where this delta VBE is nothing but our V2 term. And also one could rewrite this entire expression in terms of temperature coefficients as something like where V reference is independent of any temperature term. So when we differentiate, we end up having a zero term, and then this delta VB with respect to temperature, and alpha 2, which is again results in a positive temperature coefficient. Okay, so this is the quantity that we have already got it. Now we know that this particular quantity ends up having a value which is equal to which is approximately equal to minus 1.5 millivolt per Kelvin, and we also evaluated this quantity which is evaluated at different conditions. So which means that at the same room temperature, when we try to evaluate for an n that is equal to 10, okay, so it is only for that specific value. When we evaluate it, we end up having a factor for this which is turns around to be I think it is 0.198 millivolt per Kelvin. So as you could able to clearly see that we have towards this end we have this minus 1.5 millivolt per Kelvin has to be added to this positive term, which is right now currently is not equal to plus 1.5. So what we wanted is, in order to create a value of 0 towards the left side, we just want to add 1.5 millivolt per Kelvin term towards the right. but as we know that this quantity that we have here has only a magnitude that is quite smaller for a value of n that is equal to 10, which is quite smaller. So we just need to amplify this quantity to a value which is equal to 1.5 millivolt, right? So this amplification factor could be represented by something like a k across our delta VB, and this delta VB has to be amplified by a k factor such that the output of this will be the same as that we have it here, but with opposite temperature coefficients. Clear? Yeah. So now this is to be added along with our negative temperature coefficient, and the resultant of this would be equal to our V reference, and this V reference value, when let me try to prove this value, but as of now let us assume that this value is equal to 1.25 volt. Okay. So now let us try to understand some of the terms, and let us try to do some mathematical uh, derivations in order to really calculate these k factors and stuffs. Okay. So in this case, this k factor can also be visualized as something like an alpha 2 factor. Okay. And I am not using this alpha 2 here over here as just because the n value is fixed in this case, but in general even the n value is in our control. So yeah, so basically the k and the alpha 2 are one or the same. Okay, this is what I just want to mean. Clear? So hope that you're clear with this discussion. So symbolically I have to add this negative temperature coefficient with the positive temperature coefficient terms in order to create a V reference which is completely independent of temperature. Okay. So now let me rewrite this expression of V reference which I have written down here as V reference is equal to alpha 1 times that of VB, and in the place of delta VB, we know that this delta VB is nothing but the potential difference between the VBs of two transistors that are being operated with different current densities, right. So in that case we end up having a value which is equal to thermal voltage times that of the current density ratio factor. Okay. So this is what we have here. Now let us start evaluating this expression and try to find what is this k factor or the alpha 2 factor supposed to be. Okay. Now among this term one could visually see that this factor of alpha 2 as well as this ln of n term is basically in our control. Okay. So one has to fine tune these two factors such that we can create a factor that is equal to k, and that when it gets multiplied to this quantity we could create a magnitude of plus 1.5 millivolt when we discuss with respect to the temperature coefficient terms. So what I really mean is that the same expression, I'm just keep repeating it just to ensure that you people are all understanding it. Yeah. So what I have here is this quantity which is completely in our control, and there is a term which is delta Vt by delta V. Okay. So this is the quantity that I have, and basically we just want to evaluate what's supposed to be the magnitude of this quantity such that this quantity when it gets multiplied with this term, it results in a positive value of 1.5 millivolt per Kelvin, provided in this case if I assume that the alpha 1 is equal to 1. Okay. So we know that when alpha 1 is equal to 1, then this particular term will result in an approximated value of minus 1.5 millivolt per Kelvin. So we just need to generate a plus 1.5 millivolt out of this entire second term. Now among these entire second term, there are two sub terms that we can identify here. The first one is this quantity which is term A, the second one which is again a constant which we do not have any control over it. Okay. So this is what, so it is with respect to term A, we just have to amplify the term B such that the end result of this A into B results in a positive value of 1.5 millivolt per Kelvin. Okay. Now all of these things are under the assumption that the value of alpha 1 is considered to be equal to 1, clear? Yeah. So now let us try to evaluate this delta Vt with respect to T. Okay. Now we know that Vt is nothing but the thermal voltage, and which is defined as Kt by Q. When we differentiate that, we end up having a result which is K by Q, and the value of this result is approximately equal to a positive value which is 0.087 millivolt, okay, per Kelvin. So you might think that this value is different from what we evaluated earlier, where we had a value which is, sorry guys, got a call. Yeah, okay. So this value was a bit different from what I was been talking earlier, right? So that was basically a delta VB with respect to delta T, and we had a term which is almost closer to this, but with a ln value of 10. Okay, so that was giving us a result which is again a positive value, which is 0.198 millivolt per Kelvin, and this is the term that we have ended up. Okay, so this is different for, this is specifically for a value of n that is equal to 10. Okay, but n can be chosen differently, so we have just left over this n factor out of this equation, and we are just trying to evaluate just the factor of dou Vt by dou t term. Okay, yeah. So now that the value of this b factor is known, okay, this b factor is known. Now the only thing is that we need to identify what's supposed to be this a factor, such that when I multiply this a factor with respect with this b factor, the end result of this product supposed to be equal to this 1.5 millivolt per Kelvin, right? Yeah. So let us try to do that. We want this alpha 2 times that of ln of n times that of dou Vt with respect to temperature supposed to be equal to plus 1.5 millivolt per Kelvin, and we just now calculate this value of this alpha, sorry, this factor, which is 0.08, so that now we end up having this to be equal to 1.5 millivolt per Kelvin divided by the factor of 0.087 millivolt per Kelvin. So this approximately ends up having a result which is equal to 17.24. Okay. So this is the result that we would end up having after this. Now even here one could assume that this alpha 2 can be taken as 1, and let us try to evaluate this quantity. So if under this assumption, when alpha 2 is also taken as considered as a value of 1, then this ln of n supposed to be approximately equal to 17.4 or 17.24. Okay, and this is what we wanted, this is the quantity that we want to have across this ln of n, such that when I substitute this value onto this expression, okay, so that the product of this a and b will end up having this 1 plus 1.5 millivolt per Kelvin. Okay, so hope that you are clear. Now let me try to bring this name of the circuit that we are about to build is also termed as band gap reference voltage. Okay, so I just want to talk about it, why it is called as a band gap reference voltage. Now in order to do that, let us rewrite this expression that I wrote it before. Okay, this particular expression, I just want to rewrite this particular expression, which is, after considering this alpha 1 and as well as alpha 2 as 1 and 1, okay, one could write the negative temperature coefficient plus this k times that of q, which is the positive temperature coefficient value, which is dou Vt by dou t term, into this ln of n. Okay. So this is the value that we supposed to have, that's supposed to be equal to 17.24. Clear? Yeah. So with this, let us try to evaluate it. Now, as I said in the morning session, that one has to recall the expression of this dou VBE with respect to dou T. So let me write that expression that we have evaluated, which is dou VBE with respect to dou T, could be written as VBE minus 4 plus m into Vt minus Eg by Q divided by T. Now clearly you could able to see that there is a term which has Eg, where Eg is nothing but the energy band gap of silicon, okay, and that has been appropriately been divided by a factor of Q, so that this entire E by Q term will give us a voltage expression, okay. So that's the reason why it is written in that particular way. So in the place of dou VB with respect to dou T, I could use this expression that has been written down here, okay. But before that, let me also bring the expression from something like this, so that what I have is dou T is equal to minus K by Q into ln of n. One can also write this K by Q term in terms of Vt. So due to which I have a term K by Q, which I am just going to multiply and divide by temperature, and we know that the combination of this this Kt by Q is nothing but our thermal voltage divided by the temperature, okay. So rather than writing just as K by Q, I can replace this K by Q with Vt by T, okay. Yeah, so having got this expression, let us try to plug in the value of this dou VB with respect to dou T with this expression that I written here, okay. So on the left hand side, I have this VB minus 4 plus m, and I also stated that the factor of m is nothing but the temperature dependent parameter, and that is approximately closer to a value of minus 3 by 2, okay. And Vt is the thermal voltage divided by Q. The whole of these things has to be divided by temperature, and onto the right side we have the thermal voltage divided by the temperature into ln of En factor, okay. So there are a few common terms that we can cancel. So one of the term is this temperature term, which could be cancelled out, and we also have to recall that a V reference is nothing but VB plus Vt into ln of n, okay, assuming that this alpha 1 and alpha 2 both are equal to 1. Under that condition, this is the V reference value that we have, right. So let us try to pull out those terms out of this expression. So we have a VB term, and on the right hand side we have a negative value of Vt into ln of n, so which when we bring it towards the right, it becomes a V reference, okay. So this entire combination would result in the expression of V reference, okay, and that's supposed to be equal to the remaining term, which I could push it towards the right hand side as 4 plus m Vt plus Eg by Q, okay. Yeah, so this is the final expression that we have got, and now let us try to look across a special case here. So when this temperature is approaches a value of 0 Kelvin, now what happens is that the Vt term also approaches a value of 0, the thermal voltage will also approaches a value of 0, and due to which our V reference will approach to a value which is equal to Eg by Q, and this is nothing but a voltage value which is equal to 1.206 volt, okay. So this is nothing but the energy band gap voltage value that we were getting it, and it is because of this relation that we have, it is called as a band gap reference voltage, okay. The value of Eg by Q gives us a result which is 1.2 volt, okay. Yeah, so having said that, let us try to evaluate the V reference at room temperature. Okay. So, at room temperature means we have 300 Kelvin, and under that condition and substituting a value of m that is equal to minus 3 by 2, we have a thermal voltage which is approximately equal to 26 millivolt, and based on these values, when we try to evaluate the V reference, we end up having a result which is closer to 1.25 volt. Okay. So, this is the reason why when I wrote the V reference, I stated that the value is equal to 1.25 volt. Okay. And this combination of this PTAT, that is the complementary to temperature, complementary to absolute temperature circuit, and this PTAT circuit, the combination of both these circuits will result in what is known as the band gap reference voltage circuit. Okay. So, now let us look for the implementation part, uh, which is quite interesting to work on it. Okay. So, as we know that we have to have a reference circuit, and yeah. So, before we begin with this BGR, let us try to look for the curvature of this graph of this V reference. Okay. Yeah. Let us try to plot our V reference voltage that we have got, okay, or V reference expression that we have got here onto a temperature Cara. Okay. And let us try to mimic that this expression was evaluated for a temperature T that is equal to T naught. Okay. Now, under that particular condition, one would end up having a kind of Cara. Okay. And when we just look across the temperature T that is equal to T naught, you could see that this curvature is almost constant. The slope of this particular line is almost constant, but when we move away from this particular temperature, what happens is that the graph basically tends to deviate away from this constant V reference, just because of the factor T that is involved in these expressions. Okay. So, because of those terms, it gets deviated. Yeah. So, now let us try to build this the BGR circuit, which is based on the above discussion. Okay. So, in order to build this reference circuit, as I said, we need both these quantities or both the type of structure. First, let us try to put the CTAT circuit, which is complementary to absolute temperature, or circuit that exhibits a negative temperature coefficient. Okay. And let us mark the transistor as Q1, and this has an area of A, or an emitter area of AE, right. And let us mark the voltage that is being read across this particular node as VO1. Okay. And there is actually a current flow of I here. And let us take one more circuit which gives us, okay, yeah. So, let us pass this through a resistor, and let me mark this as R1, and then pass it through a diode connected configuration, but this time the area of this particular structure is n times greater than the area of the Q1 structure. Okay. So, let me mark this as Q2 transistor, and what we have done is that we have just created a diode connected configuration, and we have created, and we added a resistor along the path, and then we are tapping an output as VO2 here. Okay. And the current that is being passed through this structure is again is taken as I. Okay. So, hope that you are clear with this circuit setup. And now if I'll just state some of the conditions such that let us try to see where is our CTAT and where is our PTAT circuit and where exactly we are about to tap our outputs as V reference. Clear? Now, first let us look across the condition. Now, if we somehow make the VO1 to be exactly equal to VO2, that is the potential of this node and the potential of this node, if we could able to make them equal, then one could write that the VO1 is nothing but the VB of the first transistor, and that VB1 basically has to be split across two components across our VO2, right. So, basically a VO2 is nothing but it is a potential that drops across the resistance as well as the VB2. Okay. So, what I really mean is that what we have for VO1 is just VB1, but what we have across this VO2 is the summation of two potential drops. Okay. So, the first potential drop is written as R1 into I, because that is the current that flows through the collector times the VB2, right. Yeah. So, from here one could bring out this R1 times that of I towards the left side and pull out this term, so that what we have is VB1 minus VB2, and this is nothing but the potential difference between the base emitter voltages, or in short it is equal to delta VB, and we know that this delta VB can also be written as Vt into ln of n, and this n comes out just because we are using a different area, emitter area for Q2 than compared to Q1. Okay, rather than using a different current densities, we are using different areas for the emitter areas for the Q2. So, this results in a different value of saturation current. Okay. So, in case if I assume that this IS1 or the saturation current of IS1 is equal to IS, then the saturation current through Q2 is written as En times that of IS. Okay. So, that is how we can relate. Yeah. So, I hope that this phenomena is clear, and yeah. So, one could write this VO2 as this particular term and this Vt into ln of n, right, and that is the drop that we have, we could able to observe across the resistance R1 plus this VB to here. Now, clearly one could see that this is the same term that we had when we wrote an expression for V reference. So, let me try to recollect what we have, how we have defined our V reference. So, in this case V reference was written as alpha 1 times that of VBE plus alpha 2 times that of delta VBE, and we know that this delta VBE is nothing but could also be written in terms of Vt into ln of n factor, and this is what we have here. Okay. So, clearly in this, while trying to evaluate this factor of VO2, one could see that this VBE2 potential drop is nothing but our CTAT circuit, okay, or it exhibits this VBE2 exhibits basically a negative temperature coefficient, whereas the drop across this resistance basically exhibits what is known as the PTAT circuit. Okay. So, the combination of these two things with an appropriate factor, okay, and that factor results in a particular value of resistance. Okay. So, this is what we just want to see here, okay. And one could visualize the same VO2 as an expression for V reference as well. So, a V reference can be tapped directly from here based on this circuit. I hope that you are clear. So, one could write it as V reference provided if I could make sure that this ln of n factor is approximately equal to 17.24 quantity. Okay. So, that is again one more huge requirement, okay, that one has to ensure. Now, let us try to bring out this expression of R1 into I in order to express the quantity of R1. So one could see that this R1 is basically Vt into ln of n divided by the factor of I. So based on the current that is flowing through the circuit, one could define the value of R1. Okay, yeah. So now basically this circuit uh, needs a few of the modifications has to be incorporated to make the circuit to be more practical. Okay, so in order to make the circuit more practical, we need two more modifications to be done. Okay. One is a mechanism has to be added such that it guarantees that our VO1 is exactly equal to VO2. Okay. So until otherwise this is not guaranteed, whatever the derivation that we did, all these will go in vain. Okay. And the second requirement or the second modification that has to be incorporated into the circuit is that we want this ln of n factor, which is supposed to be equal to 17.24, and this in turn basically translate to a large value of n. Okay. So if you do a very simple math, the n value becomes almost closer to a value of 30 point some, I think 30.6 mega. Okay. So which means that when you compare the area of the second transistor, with respect to the first transistor, the second transistor area is supposed to be 30.6 into 10 to the power 6. Okay. So that much area has to be occupied by the second transistor, okay, which is quite large. Okay. And in an IC, this would consume the entire chip, right. So one has to think about this while designing this particular circuit. So one has to step down this requirement of n being a very large quantity. Okay. Yeah. So now there are two ways by which one could establish the first mechanism, and in turn one can also address the second requirement of translating this ln of n into 17.24. Okay. So let me try to list out what are the two circuits that one could use in order to implement these two requirements. Okay. The very first circuit uses what is known as the supply independent biasing circuit. Okay. So that is the first way by which I can ensure the same current to flow, as well as it can also ensure that our VO1 would be exactly equal to VO2. The second option that we have in order to guarantee this particular mechanism, as well as to satisfy the second requirement of making this ln of n to be a 17.24, is by making use of an op amp circuit. Okay. So let us try to make use of the first circuitry today, and let me try to explain the implementation part of it, and probably in the next class let me talk about the op amp part of the discussion in the next class. Okay. Yeah. So let me try to draw the circuit. As said, we are going to use a supply independent biasing, which means that I guess you people still remember that the supply independent biasing circuit is nothing but it's a combination of PMOS current mirror with an NMOS current mirror, but we would make this PMOS current mirror circuit to have the same WL factor, such that if I label this as M3 and if this PMOS transistor is M4, then if I could able to make this ratios of M3 and M4 to be common, then the currents that are flowing through ID3 and ID4 will also be same, right. Yeah. So based on this, and later what we did is that we just had an NMOS structure at the bottom, current mirror structure at the bottom, and we had a diode connected, and then later after this we had a structure and let me label this diode connected structure with M1 and the other transistor as M2, and if I have this W by L factor of M1 to be equal to W by L of N, then we previously had a factor of K being multiplied with the W by L of N factor. Okay. So in that case what happens is that the voltage that we have here will not be same, right. Uh, the question here is that we have to ensure that our VO1 has to be same as that of our VO2. Now in this circuit condition, if the W by L factor of M1 is not same as that of the W by L factor of this M2, then one cannot ensure that this value of VGS to be exactly equal to this value of VGS. The way that one could ensure that both these VGS1 as well as VGS2 are same is by ensuring that if they share the same aspect ratio across them, then one could ensure the source potential of M1 as well as the source potential of M2 to be same, right. So in that case one has to consider only a factor of k that is equal to 1 that has to be implemented onto this. So when we have this k that is equal to 1, then the VGS1 and VGS2 will be equal to each other, just because the same amount of current is flowing across both these branches. Okay. So this will ensure our VGS1 to be equal to VGS2, and in turn one could also ensure that VS1 would be equal to VS2. So this is what we wanted. Now after this if I translate this VS1 into what is known as VO1, and if I could translate this VS2 as what is known as VO2, then our circuit is all ready. Okay. So we wanted same current to flow, and that current has to be passed through this diode connected Q1, and the second branch should have the same current, but it is being passed through a resistance in series with the diode connected structure, right. So this is the structure that we are yet to add. Okay. Now in this addition I am just going to do some modification. Okay. So in this case you could able to see that I am still using a BGT, but the type of BGT that I am using is a PNP transistor rather than an NPN transistor that we used earlier. Okay. So in this case this structure was NPN transistor, but right now I have replaced that with a PNP transistor. The reason why this has been changed is that in any CMOS process, that is the technology that you are using, basically they support a PNP transistor rather than an NPN transistor. Okay. So in case if you are designing a BGR circuit and if the technology that you are working supports a PNP transistor rather than NPN transistor, then one could use this kind of structure in order to build that. Okay. So there is nothing further to discuss about it. The reason is a pretty simple one. Okay. So this NPN transistor in general is compatible with the CMOS technology, and we have used the CMOS transistors at the top, right, to establish this supply independent current sources. Okay. Yeah. So followed by this second branch, I have to have a resistance which I label it as R1, and then I pass it through Q2 structure, and this Q2 structure will have an area which is n times that of the area compared to our Q1 structure. Okay. Yeah. So this is the general structure that I have, and this structure will ensure that our VO1 and our VO2 will be same, and the currents that are flowing through both the branches will also be same. Okay. The only small modification that we have done in the circuit is that rather than having this M1 and M2 as two different aspect ratios, we had ensured that both have to have the same value, okay, such that our VO1 would be exactly equal to our VO2. Okay. So except for that small change, the supply independent circuit is just being placed on top of our general structure of BGR. clear. Yeah. So now in this case let us try to uh, evaluate the value of this R. Okay. So as I said before, the current that is flowing through this particular branch, okay, or through the resistance R, can be written as I, that is equal to the drop across this resistance, as I stated, is nothing but uh, it represents the positive temperature coefficient term or PTAT circuit, right. So that is nothing but delta VB, and that value of delta VB can be written as Vt into ln of n factor, and the n is taken from this particular quantity, okay, and that when it gets divided by the resistance value of R1, we would end up having a current here. But as I said before, we want this ln of n factor, and again I am going, all of these discussions were under the assumption that this alpha 1 and alpha 2 both are equal to 1, okay. So under this assumption, this we want this ln of n to be approximately equal to 17.24, and that indeed uh, results in a value of n that is closer to a value of 30.7 mega, okay. So which is a quite large area compared to this Q1 transistor, okay. So we need a Q2 with a very large emitter area. So now, so because of this particular reason, I do not want to tap my V reference out of the circuit as it is here, okay, just because I need a huge transistor for in order to implement this Q2. So now what we can do is that let us use one more mirror structure, and we will try to tap this current I through this mirror structure to one more branch, okay. So let me do mathematically and let me show that. So let me use a different color. So to this structure, I am just going to add an extra circuit just to step down this particular requirement, okay, just to cancel out this huge requirement on to my Q2. I am just doing one more circuit, okay. I am just adding an extra circuit to along with this circuit setup. So let me add a mirror structure, and let me use the value of VB that has been generated here, and let me plug in here. Now let me label this transistor as M5, and if at all, if this M5 also has the same W by L of P, then this whatever the current that flows here, which is I, which has been defined here, will also flow through this particular circuit, right. Now we know that I can also use the resistor in order to create a voltage drop. So when this current I, when it flows through a resistor R, and let me use this resistance value as R2 rather than just R, okay, then the combination of I into R will then create what is known as a voltage, okay. But still I cannot use that voltage as a V reference. As I said, the current when it flows through this R2, the R2 basically mimics only the positive temperature or PTAT circuit behavior, but we want a CTAT to be added along with it. So what I really mean is that we just need to add an extra structure at the bottom of this transistor as we had for the second branch, okay. So the same similar setup has to be added along with it, okay. Yeah. So now this in turn will give us a value of VB, and this VB is the one that we wanted in order to create this CTAT voltage, okay. Yeah. So now the emitter area does not matter here, just because the current is just mirrored from this particular branch. It is being mirrored onto this new branch of M5, okay. So we never worry about this factor of n here, okay, and it can be of same value of area that we had for Q1, okay. So it does not matter here. Yeah. So having said that, we had this combination of PTAT along with CTAT, and the only thing is that if I could able to tap an output and read what is this voltage as, it turns out to be our V reference, okay. Now let us see what is this how does this addition of R2 and the combination of Q3 structure, how does it create this PTAT with an emitter area which is quite nominal, okay. So what I really mean is that instead of having a factor of n that is equal to 30.7 mega, one could even use a factor of n that is closer to equal to 2. Okay. But I can use this resistance of R1 and R2 to create a large factor of 17.2. Okay. Hope that I am not confusing you people. Now let us assume that we have a current flow I, just for the sake of discussion. Um, let us try to evaluate this V reference. Okay. Now this V reference is nothing but the product of I into R2 plus the VB, right. So these are the drops across the resistance as well as the drop across the base emitter voltage of Q3. Now one could rewrite this I reference based on the expression that is being wrote before, which is written as Vt into ln of n, and at the denominator we have a factor sitting which is R1, and that is being multiplied with R2 times that of V reference times that of VB. Now clearly one could see that there is an extra factor that is being added along with this. So this factor of R2 by R1 is nothing but our alpha 2 factor. So in the previous case, or in this part of the circuit, in the second part of the circuit, the alpha 2 was considered to be equal to 1, but when we added this extra circuit, the alpha 2 is no more equal to 1. Okay. So one could have a large resistance value than compared to this R1, so that one could bring this entire factor to be closer to a value of 17.2. Okay. So the only requirement is that instead of having just ln of n to be equal to 17.24, now that we have this combination of R2 by R1 into ln of n to be equal to 17.24. Okay. So that one could use a small factor of n, but still can work with this ratio in order to create the quantity or the specific value of 17.24, and that is how the circuit would then work. Okay. So hope that it is clear. The added extra circuit has given us this factor of R2 by R1, which could be considered as alpha 2 factor. Okay. Yeah. So finally there is one small design problem which I will write it down here. So I just want you people to work out this. So design a BGR using CTAT and PTAT voltages for the following specification. Okay. So the parameter values are VDD, which is equal to 3.3 volt, and a DC bias current of 5 microamperes, and a factor of n that is equal to 2, and this is meant for PTAT generation. Okay. Yeah. So in this case the factor of n applies only for the second branch of Q2 transistor. Okay. Do not apply for Q3. I hope that it is clear. Okay. Yeah. So I want you to design this entire circuit based on this. So which means that for this given problem statement, one has to use this BGR, which has been built by making use of this supply independent source. Okay. Because the supply independent biasing circuit ensures that both these branches receive the same current, and in the question there is only one DC current that is being given. Okay. So probably in the next class we will discuss one more type of BGR circuit which has been built using op amp, where one could have a different current factors flowing across both these branches. Okay. So in that case both the values of current has to be given. So whenever a single current value is given, it is implied that one has to use this supply independent circuit in order to build this BGR. Okay. So with that, let me stop my stream, and people can use the Zoom link that I have posted earlier in order to have a chat with me. Thank you.